Questions from this section will be from 9.5. So let's begin with this one. And this one is dealing with the alternating series test. Alternating series test. The thing that makes something an alternating series is if we alternate signs. Positive, negative, positive, negative. It could start out positive, it could start out negative. And the piece that generates the alternating signs is when we have a -1 to a power. So anytime the exponent is odd, this is going to be negative. Anytime the exponent is even, that's going to be positive. So the alternating series test says that if we take the part that is not the alternating part, the 8n minus 1 over 3n plus 1, if that limit goes to something other than 0, then this is going to diverge. Why is that the case? Well, let's look at this example. If we take the limit of this part as n goes to infinity, as n gets bigger and bigger and bigger, this is going to go to 8/3. By direct substitution, it's indeterminate, but if we use L'Hopital's rule or any other technique, then this limit goes to 8/3, which means eventually, as n is really large, we're essentially going to have the other pieces of our sequence, let's say s sub n, and then we're going to be adding 8/3 and subtracting 8/3, and then we're going to add 8/3 and subtract 8/3, and it's not going to be exactly 8/3, but it's going to be really close to it as n is infinitely large. So if we group the other terms with this one, we would get one sum, but if we group in there, that's going to give us a completely different sum. And then if we add that one, it's going to go up 8/3 and then down 8/3 and then up. So after a while, we're going to be alternating back and forth between two totals. So it's not going to go to any particular number. It might not necessarily go to infinity, but it's also not going to converge to a specific value. So in this case, this one diverges. If we look at the next one, let's look at the non-alternating part, n over n squared plus 6. This is alternating because we have -1 to a power. The power is not just n this time, it's n plus 1, but that just makes the first one have an even exponent, where the previous one, when n was 1, we had an odd exponent. So the part that generates the numbers in the sequence is n over n squared plus 6. So if we take the limit of this one as n goes to infinity, that's going to go to 0. So after a significant amount of time, as n is really large, then we're going to have the other values in our sequence that are being added or subtracted. And then after a while, we're going to be adding basically 0 because the number generating part is getting really close to 0, and then we're going to subtract 0. Add 0 and then subtract 0. Add 0 and subtract 0. So once the remaining terms are significantly close to 0, our sum is really just going to be what we have from the preceding terms. What do we get when we add or combine all the other ones? So if we're not adding up more and more and more and more, or if we're not alternating between two different numbers, then we're settling in on near a particular value, so this one is going to converge. If we look at this one, notice this one doesn't have a -1 to the n power. So let's just look at what's happening with this one. If we put in a 1, we're going to have sine of 2 minus 1, which is 1, over 2 times pi, or pi over 2. And then if we put in a 2, we're going to have sine of 4 minus 1, so 3 pi over 2. And then if we put in a 3, we're going to have 6 minus 1, so 5 pi over 2. And then the next one would be 7 pi over 2, and so forth. If we have a formula like 2n, this gives us even numbers. If n is 1, we get 2. If n is 2, we get 4. If n is 3, we get 6. If n is 4, we get 8. Where if we have 2n minus 1 or 2n plus 1, that's going to give us odd numbers. If n is 1, 2n, or 2 times 1 is 2. The number before 2 is 1. Any number we put in, when we double it, gives us an even. If we either subtract 1 from an even or add 1 to an even, we're going to be at an odd number. Now, at pi over 2, sine is 1. At 3 pi over 2, sine is negative 1. 5 pi over 2, we're back to a positive 1. 7 pi over 2, we're back to a negative 1. So this is going to alternate between plus 1, minus 1, plus 1, minus 1, forever and ever and ever. So if we look at partial sums, the first partial sum, the first term is 1. If we add the first 2, we get 0. If we add the first 3, we get 1. If we add the first 4, we get 0. And we're going to continue that pattern forever and ever and ever. So even though we don't have a negative 1 to a power, we're still going to be alternating back and forth. When n is 1, we're at 1. When n is 2, our total is 0. When n is 3, our total is 1. Then 0. Then 1. Then 0. So if these are our partial sums, our partial sums as n goes to infinity is not converging to a specific number. It's bouncing back and forth. So this one is going to diverge. We have to be our partial sums as n goes to infinity has to be narrowing down to a specific number. Otherwise, we're diverging. If it goes to infinity, it diverges. If it goes to negative infinity, it diverges. Or if it's bouncing back and forth between two different values, it's also diverging. Then, I believe this is the last one from this section. They ask us to approximate the sum of this using the first 6 terms. So there's a theorem, there's some properties that they discuss, and they talk about error. It turns out that if we want to know what the sum of this is going towards, we can kind of get an approximation, and the error from stopping at 6 terms is equal to what the actual sum is minus the sum just through the first 6 terms. So say that again. If we take what it actually adds up to, if we go all the way to infinity, of course we can't go all the way to infinity. If we subtract the first 6 terms, then this is including the 7th term all the way through the infinite term. So this is saying whatever is left, that's how much error we have. That's what we're not accounting for if we stop at 6 terms. So this is the part that's not being accounted for if we stop at 6. It turns out that that's less than or equal to the 7th term in the sequence that generates this series. So if we find the first 6 terms and add them together, then we can find out how close that is to the actual sum of the series all the way to infinity just by looking at the very next term. And that has to do with the fact that this is alternating. We're going to add, let's see, if this was 7, 7 plus 1 is 8, so that's going to be a positive. So we would add the 7th term, and then the next value is going to be a negative. So really, we're taking it away, and then we're adding the next one, and then taking away. And the values we're adding are smaller than the previous number. The number we're subtracting is smaller than the number before that. So even though these go on forever, it's similar to something that's telescoping, but these values are going to cancel each other out as we go on farther. Not completely, but since they're getting smaller, then they're going to cancel part of it out, and then they're going to add back a little, but then they're going to cancel part of it out, add back a little. And there's not going to be a whole lot left once we do that. So if we know the sum of what comes before that, that's going to be a pretty good approximation. And the next term, the first term that's not included, is going to give us an error, the maximum amount of error that we would have by leaving those terms off. So let's do this. So if we put in a 1, we get 1 plus 1, which is 2. So negative 1 squared is 1. So we end up with 1 over 3 to the first. When we put a 2 in, 2 plus 1 is 3. I have a negative 2 over 3 to the second. Then the next one will be positive 3 over 3 to the third. Then minus 4 over 3 to the fourth. Then plus 5 over 3 to the fifth. Minus 6 over 3 to the sixth. So that's the first 6 terms. The 7th term is 7 over a to the 7th. And that we really would need to take the absolute value of that. So let's see what we get here. We could actually multiply these out if we want to, but we're going to use our calculator eventually to combine these. So we have 1 over 3, 2 over 9, 3 over 27, 4 over 81, 5 over 243, and 6 over 729, 3 to the 6th. Yeah. So now if we combine those, that's going to give us an approximation for our sum. So let's pull out our calculator. And let's do that. So we have 1/3, not half, 1/3, minus 2/9, plus 3 over 27, minus 4 over 81, plus 5 over, oops, I'm not sure my calculator is going to respond to that. Let me start over. So 1/3 is that, minus parenthesis 2 over 9. Put it in parentheses to make sure that what we're taking away is the result of 2 divided by 9. Then plus parentheses 3 over 27. And then minus the result of 4 over 81. And then plus the result of 5 over 243. And then minus the result of 6 over 729. So when we do that, I get about 0.1852 to 4 decimal places. It's about 0.1852. if you noticed, our terms were getting smaller and smaller and smaller. When we did 5 over 243, that's how much we were adding, and then we took away 6. This out. 6 over 729, which is an even smaller number. So we're taking away something even smaller. The next term we would be adding something even smaller. So to find out how much error we have, we're going to look at the next value in the sequence. 7 over, and I wrote a to the 7th here. That was not supposed to be a, that's supposed to be 3 to the 7th. So if we do 7 over 3 raised to the 7th power, 0.032, 0032. So that's how much, that's the maximum amount of error. It could be that we have less error than that. So our error is going to be either that or smaller. So they're just going to ask us for this number, but if we wanted to know what is the largest our sum could be, or what's the smallest it could be, so if this is our approximation, then our actual sum, if it's this much more, it's going to be 0.1852 plus 0.0032. If it's smaller than that, it's going to be 0.1852 minus the error. We don't know, is our error, is our distance from the actual value, is it going to be more than that or less than that? So this is how far it is. We don't know if our sum is going to be bigger or smaller. So our actual sum is somewhere in between there. So 0.1852 minus 0.0032. So 0.0, not 0.0. 0.182 if we add it to it, 0.1852 plus the error, 0.1184. 1884, if I could say it correctly. So the actual sum is, it's in between those at some location.